This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs. Also, make sure to check out and subscribe to our YouTube original channel, UCTV Prime, available only on YouTube.
Good evening and welcome to the Burge Aquarium. My name is Nigella Hilgarth and I'm the Executive Director of the Burge Aquarium at Scripps Institution of Oceanography. And it gives me great pleasure to welcome you to the latest Jeffrey B. Graham Perspectives on Ocean Science lecture series. And tonight, it's my great pleasure to introduce our speaker, Dr. Dean Remick. Dr. Remick has a BA in physics from Swarthmore College, and he got his PhD in oceanography at Massachusetts Institute of Technology and Woods Hole Oceanographic Institution joint program. And then he stayed and did a postdoc for a year at Woods Hole, and then he saw the error of his ways, and he came to Scripps Institution of Oceanography in 1981 and has been here ever since and is a professor of oceanography here. And in fact, he won in 2008, he won the Sverdrup Gold Medal Award from the American Meteorological Society for his contributions to the oceans and climate, and especially the Argo Array, which he's going to talk about tonight. And so it gives me a very great pleasure to ask him to come and up to the podium and talk to us this evening. Thank you.
Thanks very much, Nigella. I was certain I was going to forget to turn on my microphone. That's why I was sort of grasping it. So thank you all for coming. I'd like to begin by giving credit to my co-authors in the study that I'm going to talk to you about. And that's John Gilson, who's here at Scripps, and my colleague John Gould at the National Oceanography Center, Southampton, in the UK. So I'll give you a brief outline of the talk, and I'm going to start by discussing the relationship between ocean temperature and global climate. And I'll try and convince you that measuring the temperature of the ocean is a very fundamental index for the climate system as a whole. Then this talk is going to be ranging over 135 years of temperature measurements, so I'll go all the way back to the Challenger expedition, talk to you a little bit about what Challenger was and what it did, and how that marked the beginning of the global scale measurement of ocean temperature. Then you'll need to know a little bit about all the technologies of the last 135 years for measuring temperature. So I'll just run through that quickly for you. And I think my point in doing this in part is because I'd like you to share with me the feeling that progress in ocean science is very tightly coupled to technologies. And if you understand the technologies by which the measurements of the ocean are made, then you'll quickly grasp the progress we've made in the science. And that eventually is going to bring us up to the modern era with profiling floats and the Argo program. And then with all that as preparation, then we can talk about temperature changes over the 135 years from Challenger to Argo. And I might add, this study that I'm talking to you tonight, this is very good timing. If you look at Nature Climate Change, that's the cover article in the current issue. So let's begin with ocean temperature and climate, and the figure you see on the upper right here, borrowed from Kevin Trenberth, is a diagram of the way that heat flows through the climate system. And it's a bit complicated, but I think what I want to take away from it is very simple, which is there's a lot of heat coming down from the top, 341 watts per square meter of the Earth, and almost the same amount going out, both as reflected radiation and re-radiation back from the surface of the planet. And there's only a very small difference between the incoming and the outgoing radiation. Here shown is about 0.9 watts per square meter, so that's like having 100-watt light bulb every 10 meter by 10 meter of the Earth. It's a small but very persistent increase in the heating content of the system, and my point is that almost all of that goes into the oceans. Over 90% of that excess heat, that 0.9 watts per square meter, ends up in the ocean, and that's because the atmosphere and the ice simply can't absorb that tremendous amount of heat that accumulates over decades of time. So that's reason number one. It's if you measure the temperature of the ocean, you have in fact measured the warming of the climate system. Second, the warming I'll describe to you is strongest at the sea surface, and the temperature change over the last few decades has been a few tenths of a degree Celsius. I'm going to keep giving you temperature in Celsius. If you want it Fahrenheit, multiply by 1.8. So a few tenths of a degree Celsius over the last few decades at the sea surface, and then it decreases with depth down to only a small fraction of that by the time you get down to 2,000 meters. So the warming is strongest at the sea surface, and the sea surface temperature is very important. First off, as I think everybody knows who lives in San Diego, the temperature of the sea surface sets the temperature at the base of the atmosphere. So that's what we feel here in our climate. It's temperature set by the top of the ocean. And the same is true on a global basis. The ocean temperature controls the base of the atmosphere. Second, ocean temperature controls evaporation from the sea surface. And so the warmer it is, the more water evaporates from the oceans, and the stronger is the entire Earth's hydrological cycle. So if the sea surface warms, more water goes into the atmosphere and more water falls out of the atmosphere. Finally, you all know that sea level is rising. The present rate of rise is slow. It's about 1 inch per decade at present. And the warming and expansion of seawater accounts for about 1/3 of that. The other 2/3 is ice melting, adding water to the oceans, but part of it is ocean warming and expansion. So this other figure, you need to study that carefully and keep it in the back of your mind. This is a plot of the heat gained by the ocean since the late 1950s. This is from a recent paper by Sid Levitas and colleagues, came out just a couple weeks ago. There have been several papers on a similar theme. This is probably the best and most recent of the lot. And there are a couple things to take away from it. One is that few tenths of a watt per square meter of excess heat adds up to a huge amount of heat over the surface of the Earth. So we're talking about adding 24 times 10 to the power of 22 joules, and a joule is 1 watt for 1 second. And that amounts over this 50-year period to about 0.4 watts per square meter. So the 0.9 figure from Trenberth, that's today's imbalance. The 0.4 that you see here is the imbalance averaged over the last 50 years. So that's this slope. This is 0 to 2,000 meters, all the heat going into the ocean in the upper 2,000. But the interesting thing about this, and you see the error bars on this are very large early in the record, and that's because the sampling of the ocean, the coverage, was very, very sparse, as you will see. And so a lot of the trick to getting these estimates is better coverage of the oceans. And in fact, as we go back to 1960, what the bottom of this plot shows is that only a few percent of the 1 degree squares in the ocean had even 4 temperature measurements per 5 years. So this is very sparse sampling that we're talking about. Moreover, this is the longest period over which you can make any estimate of continuous temperature change in the ocean. You really can't do that going back before the late 1950s. There are 1 or 2 opportunities, like the one I'll show you with the Challenger data, where we can look at the temperature change over a longer period of time, but there simply isn't this continuous record that we have for the last 50 years. Okay. Challenger expedition, I think many of you are familiar with it. There's the aquarium has had some great online material, and I think this is a real epic voyage that kicked off the science of oceanography back in the 1870s. Challenger was a British naval ship. It was a square-rigged wooden ship. You see it's a drawing of Challenger here. It's about 200 feet long. All but 2 of the guns were removed before the expedition to make it into a research vessel, replaced by laboratories and workrooms. The captain of the Challenger was George Nares, who you see here, and there were 20 naval officers and 200 crew on Challenger. Now, I've been to sea on ships that are about the same size, and we usually have, maybe 40 people on board. So, and we go out for a month. So here we are with 200 people, and the Challenger was out for 3.5 years, leaving England in late 1872 and returning in the middle of 1876. It traveled 69,000 nautical miles in that 3.5-year period. And the track of Challenger is shown here. First in the Atlantic, then it went, unfortunately, never really got into the mid-latitude Indian Ocean. And that's too bad, because I'm going to tell you that this high-latitude Indian Ocean data I can't use anyway. Then it went on into the Pacific and did a pretty good job covering the Pacific. So coverage in the Atlantic and Pacific looks pretty good. Coverage in the Indian Ocean, not so good. I'm going to call this global scale. I think I won't call it a global survey, but a global scale survey. Okay, so Challenger made deep temperature measurements at over 300 locations. So they had a steam-driven winch with an 8mm hemp sounding line weighted down with a 75-kilogram weight. The chief scientist, Charles Wyville Thomson, wrote in the archives, one of the objects of the expedition was to collect information as to the distribution of temperature in the waters of the ocean, not only at the surface, but at the bottom and at intermediate depths. And so at over 300 locations, they simply put these thermometers onto the sounding line, lowered them over with a thermometer about every 100 fathoms, and made a temperature profile that way. Here we have some data from the Challenger. This has been converted from fathoms to meters. 100 fathoms is 183 meters. And what you see here is temperature versus depth, so down to 2,500 meters, temperature in degrees C between New York, Bermuda, and St. Thomas. And this looks very much like the modern ocean. So Challenger, in fact, made the first measurements that told us the stratification, the basic temperature stratification of the oceans, and did so very well in the Atlantic and the Pacific. I might add, in passing, the Challenger voyage was multidisciplinary, and it was responsible for not only for these wonderful temperature measurements, but also for many discoveries in biology, marine chemistry, and geology. This is a map drawn in 1935 by George Voost, and I show it to you to make the point that even by that time, which is some 50 or 60 years after Challenger, about about 20% of the stations on this map are actually Challenger stations, and the rest were not made until the 1920s and 30s. 1920s was the era when ocean research vessels were commissioned. The Atlantis at Woods Hole, the Meteor, German research vessel, and the British Discovery were all commissioned in the 20s. They all made surveys in the Atlantic Ocean. If I showed you the Pacific and the Indian, there's almost nothing. So the upshot of this, I guess, is that after Challenger, there was really quite a hiatus. And ocean scale measurements didn't really start being made again until the 1920s, largely. Okay, so here's where my story becomes progress in oceanography is synonymous with technology advances. This is the Challenger thermometer that I showed you before. It was sophisticated in some ways, and it was carefully pressure protected, which means it had a glass shell over the thermometer to protect it from being squashed under pressure. The pressure effect was on these thermometers was small, and it was measured about 4/100ths of a degree per kilometer of ocean depth. The thermometers were very coarsely calibrated, and so Wyville-Thomson noted that they could only be read to about 1/4 of a degree Fahrenheit or 0.14 degrees C accuracy. So that's a problem. And the other big problem is that the depth at which these measurements were made was only measured by the line out from the winch. So they carefully measured the length of line. They knew that it was 100 fathoms at a time. And they went to a lot of effort to try to get the sounding line vertical so that the thermometer would be at the same depth as the amount of line over the side. And so, for instance, they say in the archive the sounding line was kept quite perpendicular for 5 minutes. So they steamed around a bit in order to try to get the line vertical. But that is an issue for this discussion, because it means that the thermometer could have been at 100 fathoms, or perhaps it was only at 99. It couldn't be deeper than 100, but it could be shallower. If it's shallower, then it's going to see a slightly warmer temperature than it would see if it was down at 100. So that means that we have a small but persistent warm bias in the Challenger data. We don't really know what it is, but that means that when we go and take a difference Argo minus Challenger, that's going to be an underestimate of the actual temperature change. It's a lower bound on the temperature change since the Challenger temperatures are on the warm side. Challenger also had prototypes of more sophisticated instruments, a reversing thermometer, which I'll show you in a second. They had some test water bottles they didn't use very much, and some depth estimating gear that they also didn't use very much. So there were ideas about more technology, but really it just came down to these thermometers and measuring line out. The other problem with these thermometers was they're very much like the thermometer you put in your garden overnight to measure how cold it got to be. That is, the mercury column pushes against an index and it records the minimum temperature seen by that thermometer. You have to do something like that because, after all, you're lowering the thermometer and then you're pulling it up again, and you don't want it to be affected except by the deepest temperature, the coldest temperature that it sees. So that's the reason for using a minimum thermometer. However, it's not true. They thought probably temperature decreases everywhere in the world ocean. That's not true. And in particular, at high southern latitudes beyond about 50 degrees south, there's a shallow temperature minimum layer at about 100 meters depth. And so for that reason, the Challenger data can't be used in those regions. So that's why those high latitude Indian Ocean stations couldn't be used. Okay, let's roll time forward a little bit now. So the next real big technology advance was the use of water bottles, Nansen bottles, and deep sea reversing thermometers. So this diagram shows how a Nansen bottle worked, and it was clamped onto the wire here and had a spring release up at the top so that when a brass weight slides down the wire, it hits this release, lets go the top of the bottle, and the bottle swings from upright to inverted, as shown here. That does two things. The mechanism of the bottle is such that when it rotates, the two ends of the bottle, which had been open, letting water flow through, close. So that traps the water at whatever depth you turn it over. And it also releases a weight that slides down the wire and hits the next bottle in the sequence. Thermometers go in this thermometer case, and you see there are two of them. These are reversing thermometers, which means that when you flip them upside down, the column of mercury breaks off. And then when you haul them up, you can read the temperature that was registered on the thermometer at the time that it flipped. So that does away with having to have an index, a minimum type thermometer. So a big advance. Didn't require that temperature everywhere be decreasing with depth. Nansen bottles came into use around 1910. They stayed in use for a long time. The first oceanographic cruise I went on was in 1976. I spent a month in the Indian Ocean doing exactly this, clamping Nansen bottles onto a hydro wire and getting wet and miserable and taking them off again. This was a very accurate technology. The deep sea reversing thermometers were very finely graduated. They could be read and were accurate to a few thousandths of a degree. And you see there are space for two thermometers here. So the practice was to put a pressure protected thermometer in one place, an unprotected thermometer in the other, and by looking at the temperature difference between the pressure protected one and the unprotected one, you could calculate the depth, and that was accurate to about 5 meters. So this was great technology and was in place for about 65 years. Small digression. We're also very worried about salinity. Temperature isn't the only thing of great interest. You need salinity for a number of important reasons. The density of seawater depends on both temperature and salinity, and the dynamics, the physics depend on the density, so we need to measure both temperature and salinity. Moreover, salinity is itself a key index for climate. When it rains, the ocean gets less salty, and when it evaporates, it gets more salty. So the changes in ocean salinity have recently been shown to be strong evidence of an increase in the Earth's hydrological cycle, and this is work done using Argo data. Salinity was measured by chemical titration in the 1920s, 30s, 40s, and 50s, and then this device came along. It's to measure the conductivity of seawater, the electrical conductivity, and this was a much more accurate means of measuring salinity, and this evolved into the modern salinometer, which is used today. And these things operate by taking a sample of standard seawater that you see here, then a sample out of the Nansen bottle, and very precisely measuring the ratio of electrical conductivity between the standard and the sample. So that's how salinity came on. So having determined that both of these things then could be measured electronically, temperature using a precision resistance thermometer, and salinity by conductivity, this device was first deployed in the late 1960s, an electronic conductivity temperature depth recorder, or CTD. And these things, this was a great improvement. I mean, if you're used to standing out freezing to death, putting Nansen bottles on the wire, and now suddenly you can sit in the lab, you can put this instrument over the side, you watch it trace on the screen of temperature and salinity. You don't just get measurements where you put a water bottle on the wire, but rather you get continuous data all the way through the water column. So this was a great thing. It's still in use today. These things were developed over 15 years or so into very accurate measures of temperature, salinity, and depth, about 2 millidegrees, about 3 parts per million in salinity, and about 5 meters in depth. They're often deployed with water bottles still, so that other kinds of measurements besides temperature and salinity can also be made. The real culmination of the CTD era was the World Ocean Circulation Experiment in the 1990s. And this experiment consisted of CTD measurements along all of these ship tracks. This was the first real global survey, and in fact, this is the only real global survey of the oceans that's ever been carried out. This was in 1991 to 97, and it obtained about 8,000 CTD profiles from the sea surface to the sea bottom. So that's a real landmark expedition. Now I have to back up just a little bit in time, and it's not going to be obvious until probably the next slide where I'm going with this. But in 1955, John Swallow, who's shown here, came up with the idea of very precisely ballasting an instrument so that it could be put in the ocean, it would sink to a predetermined depth where it would become neutrally buoyant and it would stay there. It had a sound source in it, and so the ship, this is the Discovery, the ship's cat is watching John carefully. The ship would follow it around, and it could hear the pings made by this instrument, triangulate its location by steaming around and getting the pings from different angles, and thereby follow this thing as it mapped out the deep circulation. So this was one of the first great instruments for looking at the deep velocity of the ocean. Ships, even then, were very expensive, so the Discovery and John Swallow didn't want to keep chasing this float forever. So the technology was developed into much louder sound sources, like you see here. You can see this thing that's a person, that's 2 people there. This thing is quite large. Basically, you're looking at an organ pipe that made a very loud ping that could be heard from distances of 1,000 kilometers or more. So you put these in the ocean, they make a very loud ping, and you put moorings out in order to triangulate the time difference between the ping and when it's received at the location of the moorings. And that tells you where this thing is going. This is a SOFAR float. But the purpose of both of these instruments was to measure ocean current. It had nothing to do with temperature. So why am I telling you this? Okay, so a little later, in the early 1990s, Russ Davis here at Scripps and working with Doug Webb came up with the idea that why not put floats anywhere, and as long as we can get this thing to return to the sea surface, then it could be tracked by satellite and we'd know where it was. So if it starts on the sea surface, goes down, drifts for a while, comes back up again, the satellite position at each of those points tells us what the drift is at 900 meters or wherever this thing has become neutrally buoyant. So this was a great invention, and I guess only a few years after, Davis and Webb said, well, as long as we've built this thing, which is going up and down, why don't we put a CTD on it? And so that's this thing. It's exactly the same as this earlier neutrally buoyant float. This one has a CTD on the top, and this is now the modern Argo float. And I just want to show you this fun little animation made by the, the AV group here at Scripps. In case I've confused you so far, this is a nice little movie about how floats work. So first this thing is going to get deployed, splash into the water, down it goes. You're going to get some insight here into how this thing works in just a second. Okay. So here's really what it's about. There's a pump, a single cylinder pump inside the instrument, and it pushes mineral oil from its piston, its cylinder, into a rubber bladder that's outside the float, underneath. So by pushing oil into the bladder, you increase the volume of the whole float, and that makes it go up. Or if you pull the oil back into the cylinder, that decreases the total volume of the float. It becomes negatively buoyant and it goes down. So that's the guts of this thing. That's how it goes up and down, returns to the sea surface periodically, and then goes to mid-depth. A related technology, and I hope some of you may have seen The Economist this week. It had a very nice article on gliders. Gliders are, I think, they're very sexy, but have less uses, quite frankly, than floats. But they do have some very important uses. So the float, which we'll now call the Argo float, drops down to a depth of 1 kilometer. It stays and drifts there for about 9 days. Then it drops further down to 2 kilometers depth, turns around and comes straight up to the sea surface, and that's on that upcast, that's where it measures, using its CTD, salinity and temperature, and sends back, as soon as it reaches the sea surface by satellite, the data from that profile. And here you see a typical temperature profile and salinity profile. This is on the equator. This was kind of an extraordinary float. It was deployed a little over a year ago, went 3,000 kilometers west in 6 months, and then it turned around and it's made it almost all the way back to where it started. And in doing that, it's along the way, it's collected a temperature salinity profile every 10 days. Now, this is a very cost-effective technology because we've gotten rid of the ship. You know, it has to be deployed. You have to get it out there somehow, but you don't have to sit around and burn ship time every time you get a profile. So the cost of a single profile in Argo is about $200. The cost of a WOS profile was about $15,000. So that's really what makes it affordable. It's getting the ship out of the equation. So as soon as this float was designed, a number of colleagues and I looked at this and we said, we really need to do this globally. We looked at the technology, said this is great for global science, let's put out a global array. And this was the concept diagram which I drew in 1998. We thought this is what Argo should look like. And this is what Argo looks like now. I think we've come reasonably close at this point in matching the concept, the growth over the years, in the number of floats. I see it's almost impossible to read this scale, but we're up to, this is 3,300, I think, this dashed red line, and we got over 3,000 floats in 2007. So these things last about 4 or 5 years. We're trying to get them to last longer. We have to replace a fifth or a quarter of the array every year, and this is what we did, for example, in 2011 with new floats. And both of these figures show you floats that are, the key here is the country who's put them out. And there are 30 nations deploying Argo floats as part of an international program that's I think that's been the most fun of all in this, has been to see how like-minded scientists can sort of go together and get something quite large done. And that's my reason for showing you this collage of photographs. It's to make the point that no single institution, no single nation could have done this. It's a 30-nation collaborative program. Here we have Japanese colleagues who are deploying a Canadian float. Here we have New Zealand colleagues deploying a US float, a French float, a German float, and a float at the end of the rainbow. We've had good political support from, I think, all parties in the US. Argo was begun in the Clinton administration. Here you see Stan Wilson of NOAA explaining Argo to President Bush. Argo got good support and grew during the Bush administration, and it continues on under President Obama. So I think we've had good success so far in interesting all parties in the program. And there's been high-level political support elsewhere. This is my colleague Susan Wafels in Australia explaining Argo. There's the Argo float, and this is Prime Minister of Australia, Julia Gillard. Getting floats into the water has been challenging. I would love to point out the contribution made by our New Zealand colleagues. This is a 90-foot research vessel, a tiny research vessel. It's made all of these trips to South America, to South Africa. This one ship has deployed 1,000 Argo floats, a greater contribution by far than any other ship. And indeed, this individual, John Hunt, has deployed over 500 himself. I think Argo has changed global oceanography, and this is a plot to show you. This is, I've picked a fairly dramatic example. We've never been good at sampling either the southern hemisphere or wintertime. Oceanographers don't like going to sea in wintertime. So this is winter in the southern hemisphere. This is all of the temperature salinity profiles to 1,000 meters ever collected in the month of August in the southern hemisphere. Not that good, is it? And this is 5 years of August Argo profiles. So this is my point as far as technologies and technology development. Challenger, working very hard, was able to collect 300 profiles in 3.5 years. WOS, 8,000 profiles in 7 years. Argo, 10,000 profiles per month. There are many applications of Argo. I'm going to go through this very quickly. Research is perhaps first and foremost. Over 1,000 research papers have now been published using Argo data, and over 220 last year alone. The topics are very broad. A lot of it has to do with climate. Much of it is real basic research in oceanography. There are also important operational applications. The modeling centers that run either ocean models or coupled climate models are all very happy to have Argo data. If they didn't, Argo's the blue dots here. This is 1 month of sampling ingested by one of these 15 operational models. Argo dots are blue. All the other data available to them is in red or green, so there isn't very much else on global scale. I think education is a terribly important application of Argo. I think we're just scratching the surface on this. We have education programs in a number of countries who are developing curricula that will use Argo data, and we're also providing a number of education outreach tools This Global Marine Atlas is actually something you can download this off the internet. You can plot Argo data with it. You can have a lot of fun exploring the global ocean, and I urge you to give it a try. And there's also an Argo layer in Google Earth that you can easily download. Argo's future, we're not going to keep it constant, but rather a new generation of Argo floats is 30% smaller. You see one of the new small floats. This is a Scripps float, 18 kilograms instead of 30, and it will last not 4 or 5 years, but 6 or 8 years. Similarly, a new French float. This is a Japanese float, the Ninja, developed by Jamstec. And all of these are new generation floats. There's high bandwidth communication. There's basically each float has a cell phone. It phones home, and communication is very quick, faster than it used to be. So these guys spend 15 minutes on the sea surface instead of 10 hours. And the sea surface is where all bad things happen to floats. So this is great. Coverage is expanding. Future floats will profile to the ocean bottom, 6,000 meters. We're working on those now, and they'll carry new sensors, dissolved oxygen, pH, chlorophyll, carbon, nitrate, as soon as those sensors are stable and ready. Okay, I'll bet you thought I was never going to get around to this. Here's that same temperature section. You see it here. The spots are the locations where Challenger made a temperature measurement. And what you see is the result of having interpolated Argo temperature to the same location and the same time of year. So we've taken out the seasonal cycle. We simply have Argo minus Challenger. Red spot means it's warmer in Argo. Blue spot means it was warmer in Challenger. So there's lots of variability in the ocean. That's the thing about the ocean. It's a highly varying place. There are both blue spots and red spots, but I think you can see there's a predominance of red. The average here is red, and that's best seen if we look at the global maps. So this is all of the sea surface temperature differences. And this isn't that exciting because there are other measurements of sea surface temperature, but it's a good check. Here's a global time series of sea surface temperature. This is the so-called NOAA reconstructed SST. Argo era is back here, about 19.9 degrees for the global average temperature, and about 20.45. So around 0.55 degrees temperature difference between Challenger time and Argo time. There's actually slight cooling until about 1910, and then uniform warming since then. So what do we see with Argo? The mean difference is 0.59. The error we attach to that is about 0.13, and that error is based on knowing that about 100 of these 300 stations are statistically independent of each other. So we use that to construct the error. So this part of the story says that the Argo minus Challenger sea surface temperature difference is consistent with the historical SST record. But what's more interesting then is to drill down into the ocean interior. As I said, there's a measurement every 100 fathoms. Here we are at 200 fathoms and 500. And I think what you can see is that there are still more reds than blues, but it's getting less. The warming signal is less prominent than it was in sea surface temperature, and it's still stronger in the Atlantic and weaker in the Pacific. At 200 fathoms, we're seeing 0.39 degrees of temperature difference is the mean, and at 500 fathoms, 0.12. So it's decreasing from that surface value of 0.59 down to 0.12 at 500 fathoms, which is 900 and some meters. And remember what I told you earlier, that is, because depth was estimated from measured line out, this is a lower bound on the actual temperature difference. Some of these, I would bet, are too warm in the Challenger data. And the places where they're too warm become blue spots in the difference. And there are blue spots typically where we know there are strong ocean currents, where it would be very hard to maintain a perfectly vertical wire angle, like on the equator, where there's a strong equatorial undercurrent that Challenger did not know about. So put that all together, here it is, 0.59 at the sea surface. This is now depth. Temperature difference, Argo minus Challenger, decreases with depth. The error bars are shown in red here. There's an interesting dip at 100 fathoms, and then it comes back up again, and then decreases down to zero, somewhere around 1,600 meters. If you apply the measured Challenger pressure correction on the thermometers, it just changes things a little bit. It moves from the red over to the blue line. So that's corrected for pressure effects. The average temperature difference that we see in this upper 700 meters is 0.33 degrees. That's almost exactly twice what was estimated by Sid Levitas for the last 50 years. And I think that's very powerful evidence that, in fact, the warming of the oceans did not begin 50 years ago, but rather has a time scale of about 100 years, much like the sea surface temperature record. Moreover, to support that, we also find that both the Atlantic temperature change and the Pacific temperature change are about twice in the Argo minus Challenger record that's seen in the last 50 years continuous record. Really finished now, and I just thought I'd show you this as a postscript. This comes from my colleagues Will Hobbs and Josh Willis up at JPL. Now, they've looked at the difference between the Argo era and the Challenger era in IPCC CMIP-5 climate models. So these are the most sophisticated coupled models of the climate system. I'm particularly impressed by this because I know that the climate models aren't very good. This is the Argo minus Challenger difference, and what they've done now is average all the measurements against latitude. So they averaged both the Atlantic and the Pacific measurements at 30 south or 40 south up to 30 north or 40 north, and this is the temperature change that we observed in Argo minus Challenger. I think this is probably an artifact of the equatorial undercurrent causing a depth error in the Challenger thermometers. This is a climate model from the Geophysical Fluid Dynamics Lab in Princeton, New Jersey. These look remarkably similar, I think, in both amplitude and in pattern. I think it's very impressive. I haven't seen anything like it before. And indeed, our measured Argo minus Challenger temperature difference is shown here in red, and the mean of these three climate models is shown in orange. It even has that minimum, that dip at 100 fathoms and increase below it. So these two really track each other very well. And they also ask the question, which is very important, what's the difference between the temperature difference along the track of the Challenger and the actual global average? And so in the case of these models, the actual global average is this black line. That's what the models predict. I think the models tend to underestimate the temperature difference. You can see that perhaps in the difference between the orange and the red, and I suspect that this black line is also an underestimate. So that's it. I hope I've convinced you that progress in oceanography follows largely from the development of new technologies that are not only accurate but also cost-effective. The longest possible instrumental record of ocean temperature is that spanned by the 135 years from Challenger to Argo. Nobody can beat me on that. There's no longer record possible unless we just wait for more years of Argo. Although Challenger was sparse and of lower accuracy than Argo, the nice thing about a trend is if you wait long enough, you can see it even with poor instrumentation. So this is why people haven't looked at say, WOS minus Challenger. They needed to wait another 20 or 30 years for the trend to be large enough that it really stands out above the noise. The top 700 meters of the ocean has warmed by an average of about 0.3 of a degree C, twice the change seen in the last 50 years, providing strong evidence that global warming began at least 100 years ago. And this is consistent both with the sea surface temperature records and with the coupled climate models. Argo remains a key data set for global change studies, now providing 120,000 temperature salinity profiles a year. At the end of this year, we'll collect the millionth Argo profile. The coming decade will see Argo extended into the deep ocean, the marginal and coastal seas, the seasonal ice zones, and including new biogeochemical sensors. And I'll just conclude by going back to this plot that really emphasizes, I think, that this is not only a large but a multinational effort. Thank you very much. Okay. The question is, if temperature change has been seen for 100 years, what could have caused it? And I can give you two answers to that, really. The one is my cop-out answer that, I don't know what caused it. I just measure temperature. But I think it is true that the way the coupled climate models work is on the basis of CO2 greenhouse warming. This began to be put into the atmosphere back in the mid-1800s. So it is the case that the models show already 100 years ago the start of climate-related warming. Yes? So the question is, will this be fed into the new supercomputer it's being built in, was it Wyoming? Yeah.
I think it's called the Yellowstone.
And I heard they're putting it there because it uses so much electricity, they want it to go where electricity is cheapest. So the answer is yes. As I said, there are many operational models, including one at the National Center for Atmospheric Research that operates that new supercomputer. All of these ocean and coupled models are ingesting all of the Argo data. They're not ingesting Challenger data, though. So the Argo data is going in.
To add on to that, I noticed there was no Argo instrumentation going into the Gulf, and we keep hearing on television that the temperature of the water in the Gulf is affecting the weather in the United States. So
there are a few instruments in the Gulf of Mexico.
really, I didn't
See those green dots? 1, 2, 3. There are 3 floats in the Gulf.
One only one?
3.
Okay, 3.
Yes.
I'm intrigued by how these floats maintain their depth, and I take it that your Argo floats have an active system that keeps depth. How did the Swallow float keep its depth?
The thing I didn't tell you is that the way they managed to find a neutral depth where they're neutrally buoyant is because the instrument, which is metal, is much less compressible than seawater. So the neutral depth is based on the fact that as they go down, the density of the instrument doesn't change, but the density of the water around it does. And so it's that density, boy, I really can't see. It's that density difference that allows both the modern float and the Swallow float, once it's found its neutral depth, to stay fairly close. There's some creep in the metal as the metal is compressed, so it may very slowly drift deeper. But other than that, pretty well follows a constant pressure surface.
Question way in the back.
Yeah, so the question is, what happened to the Challenger thermometers? Fortunately, they did keep most of them, and another thing I didn't tell you was there were actually two sets of measurements of the pressure effect on these instruments. One was carried out before the Challenger cruise and was done erroneously, and came up with an overcorrection. Peter Guthrie Tate was given the captain and chief scientist really didn't believe this data. They kept thermometers, so after the Challenger cruise, a much more careful set of measurements was carried out using about 30 of the thermometers. So they were certainly preserved that long. I would bet that the National Oceanography Center in Southampton probably still has some of those instruments, a few of them, but I don't know.
Maybe one more question?
What's the size of the Argo program and annual funding? Well, the U.S. is responsible for about half of Argo. The U.S. funding is $10 million a year from the National Oceanic and Atmospheric Administration. There are 5 U.S. institutions that collaborate to do Argo. I'm the lead principal investigator, but Woods Hole, University of Washington, and 2 NOAA labs in Seattle and in Miami are all involved. So US 10 million, I hope we're able to keep that. I don't know. Things are getting a bit iffy these days, but our international partners are putting up a similar amount, and some of them have had great success. For example, our Australian partners and our European partners are doing very well also.
Dean, thank you for a wonderful, wonderful talk. Thank you very much.